Experiments have been conducted in a 200 feet long, 10-inch diameter pipeline to measure turbulent dispersion of chlorine solution injected near the wall of the pipe. The pipeline is arranged with a 120 pipe diameter inlet length to assure fully developed turbulent flow, and is provided with discharge measuring equipment, pressure measuring taps, and concentration sampling devices. The sketch represents a part of the pipeline, including the test section. Chlorine solution is injected at the point marked 1, 120 diameters downstream from the beginning of the 10-inch diameter pipe. The dispersion pattern can be observed at the points marked 2 through lucite viewing boxes. At the points marked 3, samples are taken at 1-inch intervals across the horizontal diameter by means of a pitot cylinder. The basic fluid in both the pipeline and nozzle is water, but potassium permanganate has been used to mark the injected fluid so that it will be visible in the film. In these pictures, the flow rate of the injected fluid has been adjusted so that its speed is the same speed as that of the water flowing in the 10-inch diameter pipe. Injection is normal to the main flow through a nozzle 1/20th the diameter of the pipe. The following scenes are shown at 3/8 normal speed and show dispersion within the first 6 diameters of injection. You are looking horizontally at the flow. In this and the following scenes, the pipe velocity is 5 feet per second and the injector extends 3/4 of an inch into the pipe. A single injector is located on the horizontal diameter of the pipe. You are now looking vertically upward at the flow. There are 2 injectors from opposite sides of the pipe. The 2 injectors are extended to 1 1/2 inches. In this and the following scene, the velocity has been increased to 10 feet per second. The nozzle extensions are 3/4 of an inch and 1 1/2 inches. Four injector nozzles extending 3/4 of an inch into the pipe are in use. The view is horizontal and the pipe velocity is 10 feet per second. 2 nozzles are 52 degrees above and 2 are 22 degrees below the horizontal diameter. 2 nozzles 30 degrees above the horizontal diameter were tested for the same flow conditions. Observe the large area of zero concentration in the lower half of the pipe. Concentration profiles were measured by injecting chlorine solution through the nozzles. The operator obtained samples of the flow through a pitot cylinder by withdrawing fluid at approximately its local velocity and titrating the sample to obtain the chlorine concentration. Samples were obtained near each wall and at 1-inch intervals across the pipe at successive sampling stations downstream from the injection point until a station was reached at which a relatively uniform distribution of chlorine across the pipe was obtained. The pitot cylinder is moved to a new position in the pipe and a new sample taken. Observe the relatively uniform distribution of dye in the second viewing box. The graph shows the change in the chlorine concentration profile as a function of the distance downstream from the injection point. The distance is expressed in terms of pipe diameter. This graph shows the ratio of the minimum to maximum chlorine concentration on the horizontal diameter as a function of the distance from the injector for various injector configurations. Comparison of curves 2 and 3 indicates that 2 injectors on the horizontal diameter result in essentially as rapid chlorine dispersion as 4 injectors. Additional experiments were performed on a small full-scale injection nozzle, a special water tunnel in which it was possible to simulate a typical pipe boundary layer of a larger pipe was used. With the flow through the tunnel set at 5 feet per second, the supply to the nozzle is activated. The tunnel flow represents a mean velocity of 5 feet per second in an 8 feet or larger diameter pipe. The nozzles tested were 2 inches in internal diameter and extended 6 inches into the flow. The speed of injection is 5 feet per second. The dispersion pattern near the nozzle is shown in the following scenes at 3/8 normal speed. The dispersion pattern using a cylindrical injector nozzle. Is compared with that using a streamlined injector nozzle. Note the similarity of the dispersion patterns. Forces and vibrational frequencies were measured on the cylindrical injector. A sensitive strain gauge dynamometer was used in measuring the vibrational characteristics. The nozzle is supported entirely by the dynamometer. A Sanborn recorder is used to record the output of the dynamometer for later analysis. The tunnel velocity, which was initially 5 feet per second, has been increased to 7 1/2 feet per second. In the graph, force and vibrational frequency are plotted as functions of tunnel velocity. The tests indicate that the vibratory forces would be of such small magnitude and in a frequency range far enough removed from the natural frequency of the prototype injectors that damage to an injector is unlikely to result from dynamic forces.